Chapter 3, Structure and Stereochemistry of Alkanes. In this chapter, we will learn more about alkanes, and we will also be visiting the rules how to name sophisticated alkanes beyond the straight chain alkanes. And in addition to that, we're also going to be looking at how conformations of alkanes are usually drawn, which is the Newman projections. And once that's done, we're going to be looking at the same thing, but the cyclic alkane category, where we're going to be given the set of rules how to name cyclic alkanes and how to draw these cyclic alkanes in 3D fashion. So alkanes are a group of hydrocarbons. They have the chemical formula of CnH2n plus 2. And we already learned that carbons usually have the 4 bonds. So that means I'm going to be having the number of hydrogens, the max for a certain number of carbons. So if I have that category, if that been fulfilled, where the maximum number of hydrogens been in a formula for a certain number of carbons, that means I'm dealing with a saturated hydrocarbon, hydrocarbon. For the cyclic alkanes, the alkenes, alkynes, all these compounds, you're going to find that the number of hydrogens are usually less than the maximum. Therefore, these structures are unsaturated. So for alkanes, you will basically be required to know the names of the simple alkanes from 1 to 12, So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, and dodecane. So these 12 are required from you to know in order for you to figure out the branched ones. You wouldn't be able to tell the sophisticated ones if you wouldn't be able to tell the more simple ones to start with. Now these alkanes, they usually have basically different ways of drawing them. For example, if I have, 4 carbons, I could be drawing them in a straight chain, or I could be drawing them in a branched format. So this branched form will basically be a constitutional isomer of the other. So that's the difference between the two. So different connectivity for 2 same chemical formula will basically have the constitutional isomerism phenomena. Constitutional isomerism formula. Sometimes we could refer to this as structural isomerism, which is the same exact thing. Here's another example of C5H12. You can see here the 5 carbons attached in a straight chain, while this one has a branch, while this one has 2 branches. So the difference between these are basically that they are constitutional isomers. In terms of physical properties, the more straight chain one will always have a higher boiling point, higher melting point than the branched ones. And we already learned that from previous lecture, where we said the intermolecular forces will be weaker when you have branched alkanes compared to straight chain alkanes. IUPAC, that's what we use to name alkanes. And every single organic compound, the very first rule is always finding the longest chain of carbons. So the longest chain of carbons in this molecule, for example, you could see that it is going to be 1, 2, 3, 4, 5, 6, versus the other way where you would have 1, 2, 3, 4, 5. So the very first step in the IUPAC set of rules to name alkanes, finding the longest chain of carbons. And it's always be the first requirement. You have to have the longest chain of carbons for a compound. And that will be the parent name. So when you figure out it's a 6-carbon chain, you know right away it's a hexane parent name. Next, what would you do? Well, let's look at another example where you will have basically 7-carbon chain versus 7-carbon chain. So looking at these 2 molecules, you will say, all right, well, I have a 7-carbon chain here versus the 7-carbon chain here. Which of the 2 is more correct? Always look for the longest chain of carbons that's going to have more branches, more substituents attached, because that's going to make the name as simple as possible. So here you have a branch of a branched group, while here you have basically more simple substituents attached to that longest chain of carbons. So that's just an example where you may face having longest chain of carbons in the same molecule, and you will be debating which of the 2 is the correct longest chain, the one that's going to have more substituents attached. So you will also, once you find that longest chain of carbons, you're going to look for the second rule. The second rule is numbering the chain. Numbering the chain will always be from the side that's closer to the nearest substituent. Or keep in mind that I want to have my substituents on carbons that are numbered the lowest numbering possible. Here's an example. You could see here that you have 1, 2, 3, 4, 5, 6, 7. Or you could have the other way around, 1, 2, 3, 4, 5, 6, 7. Which of the two is correct? Well, where are the substituents here? The substituents here are sitting on 3, 4, 5, and 6. But the substituents here are sitting on 2, 3, 4, and 5. So the lower numbering for the substituents is the way to go when you basically apply that IUPAC the third rule, which is once you find the longest chain, you're going to number the chain, basically giving the substituents the lowest numbering possible. That's very important to keep in mind. So that will be the way how you number the chain, from the side that's closer to the nearest substituent, or the numbering of the substituents to be the lowest numbering possible. Okay, keep in mind that those substituents are alkyl groups, because the alkane will always be different from the alkyl group by one hydrogen. CH4, when I take the hydrogen off, it's a CH3. So that tells me right there that I'm not dealing with an alkane, I'm dealing with an alkyl group. What's the alkyl group of methane? Methyl. What's the alkyl group of ethane? Ethyl. What's the alkyl group of propane? Propyl, and so on. So the alkane, once hydrogen is missed because of the branching bonding, that basically makes it an alkyl group, no longer an alkane. So the groups that I was looking at here are basically substituents. So I have a methyl, ethyl, and 2 other methyls. So how do I know that these are substituents? They are connected to the longest chain of carbons. So anything that's coming off the longest chain of carbons will automatically be considered a substituent. All right, what would the rule next be? Once you label those substituents, and you need to basically be familiar that it cannot be just methyl, ethyl, propyl, butyl, or pentyl. You may have branched alkyl groups. What is that supposed to mean? For the methyl, there is no branched form of it. Ethyl, there is no branched form of it. However, when you have a 3-carbon substituent, which is the propyl group, this propyl can be connected different, meaning the branching can be from the terminal or can be from the middle. So I have a 3-carbon chain that's an alkyl group, but is no longer attached from the terminal side. It's attached from the middle side. That makes it an isopropyl group. It's no longer a propyl group. So it's important to keep in mind that the isopropyl group is always going to be 3-carbon attached from the middle carbon, from the 2nd carbon. Same applies to the 4-carbon substituents. 4 carbons can be basically the branching coming from the terminal, and that makes it a butyl. Can be coming from basically a group where it has an isopropyl attached to that CH2. So you have a 4-carbon chain, but that 4 carbons, you have the isopropyl attached to a 4th carbon where the branching is. So that makes it an isobutyl. Isobutyl. 6-butyl is when you have the attachment from the 2nd carbon, and terbutyl is when you have basically 4 carbons and the attachment is coming from the middle carbon. So you have 3 methyls attached to a carbon. That makes it a 4-carbon group, but that group will be a substituent. Then it will be named a terbutyl. So you are required to know the butyl group, isobutyl group, 6-butyl group, terbutyl group, isopropyl group, propyl, ethyl, and methyl. Nothing beyond that. So you are required to know these examples of alkyl groups. And once again, you are required to know that in order for you to basically properly name the alkane at the end. So in this case, once I figure out that I'm dealing with methyl and ethyl and 2 other methyls, how am I going to go about the final name of this compound? Well, the final name will be listed alphabetically. The group's going to appear alphabetically with the position where they are in the structure, and ending the name with the parent name, which is whatever corresponds to the longest chain of carbons. So in this case, what do I have? I have ethyl and methyl. So alphabetically, ethyl will be the one that's going to show up first. So 3-ethyl, because it's carbon number 3. Then hyphen, I have multiple groups of the same. So I don't list them separate. I list them using Greek prefixes. So the Greek prefix would be, in this case, tri. So 2,4,5 indicating where they are. So 2,4,5 trimethylheptane. So the name would be, once again, once you figure out the longest chain of carbons, once you number the chain from the side that's closer to the nearest substituents, or the numbering system that's going to give you lowest numbering possible, then you name the structure by listing the substituents alphabetically with the position where they are in the structure. Here's another example. We could see here that I have the longest chain of carbons is 6 carbons. So I have this side. If I start from it, it's going to be the closer to the nearest substituent, while here is going to be further away. So if I number from the right-hand side, it's going to give me the first substituents to be on carbon number 3. So definitely has to be from the left-hand side to the right. So the 6 carbons will correspond to hexane. And I have 2 substituents. I have a methyl and ethyl. So ethyl will show up first. So I'm going to have 4-ethyl, 2-methyl hexane. This is important to keep in mind, that you're always going to have to list the substituents alphabetically. If they are the same, then all what you need to use is the Greek prefix that corresponds to the number. So what I have, if I have 2, then it's a di. If I have 3, then it's a tri. If I have 4, then it's a tetra. If I have 5, then it's penta, and so on. So these are the Greek prefixes that we're referring to when you use those in the name that has multiple groups of the same, And as I mentioned, the iso it's basically isopropyl, isobutyl. So when you label the substituents, like in this example, if I label the substituents, if there is an isopropyl versus a propyl, well, which one would be first? Well, isopropyl, you will need to look at the I versus the P in the propyl. So isopropyl is one word. That's what you need to, how you handle the isopropyl in terms of listing it alphabetically. That's different when it comes to the other alkyl groups, terbutyl, cycbutyl, or the N-butyl. N-butyl, cycbutyl, or terbutyl, these are prefixes that don't have a role in alphabetical order. Meaning, if I have a terbutyl group, I need to basically base it on the B letter in that terbutyl. Cycbutyl, you're still going to have to consider the B. So if I have a cycbutyl versus a methyl, the cycbutyl will be listed first in the name before the methyl. If I have an ethyl group and a terbutyl, the terbutyl will be listed first in the name before the ethyl group. So that's really important to keep in mind. Okay, that the isopropyl, isobutyl are the only 2 groups that you're going to consider the iso as part of the name, as part of the alkyl group name. But the other prefixes where ter, cyc, and N show up, they do not have a role in alphabetizing the alkyl group. You will have to consider the main group name, which is the butyl in all of these except the isobutyl. Okay, so here's another example. So you could see here that we have an isopropyl group of this longest chain of carbons. Longest chain of carbons is 8 carbons. So you have octane, and when you number the chain, you're going to find it to be basically giving you the lower numbering from the left to right rather than right to left, because right to left will be carbon number 5, but left to right will be carbon number 4. What do I have? I have an isopropyl, so it's going to be 4 isopropyl octane. Here's another one. We're going to have the terbutyl, so it will be named 5-terbutyl decane because it has 10 carbon chain. And here's the example that we just seen earlier. Complex substituents. I'm just going to cover this part to basically give you the knowledge of what they are about. I'm not going to be asking you a question on the quiz or the exam in regard to complex substituents. So if I have a group, this whole group as a substituent, so that means I have a branch of a branch. So how do I treat this? The branch will be basically numbered as the finding the longest chain of carbons, like in this one. So let's assume that this whole thing is attached to 10 carbon chain. Well, whatever coming off the 10 carbon chain will be numbered 1, and then you're going to have to look for the longest chain of carbons, finding that longest chain of carbons with the more branched possible. So what do I have here? I have carbon number 1 has an ethyl, carbon number 2 has a methyl. So this whole substituent will be named 1-ethyl 2-methyl propyl. 1-ethyl 2-methyl propyl. And the propyl group is the main substituent coming off that longest chain of carbons. Here's another example where you have 4 carbons coming off the longest chain of carbon. So this is a branched substituent where you're going to have to use the complex substituent format, where you're going to be numbering the chain of that branch, starting with the carbon that's directly attached to the longest chain, and that will basically give me the substituents basically sitting on carbon number 1 and carbon number 3. And as you see here, it's a 1,1,3 trimethyl butyl group. So the butyl group is the substituent of the longest chain of carbons, where the methyls are substituents of the main substituent. So that's what we consider a complex substituent as well. So next time we will be talking about conformations of alkanes. This topic is going to teach us how to visualize those compounds in space, in 3D fashion, so in space. And we will be looking at different forms of alkanes to basically understand what conformations are about. And that's all what I'm going to talk about in this part of chapter 3.